Right. So let's go to the more computational stuff. Okay. So we say that okay. So given a function f and a point we say that limit of f as x gets closer to a in the notations is L means all right, so these notations. All right, so that means the value of f can close and closer to L by taking x closer and closer to A. Okay. So that means he was approach of the value of f gets close to L as x gets close to A. Right. So this kind of computation is actually a process. Okay. All right. Let's do some simple things. Okay. So let's see. Simple limit if x goes to A. This is a, say, 10 or 9. So, okay. So does it tells you pictorially, this looks like this is a constant functions. Okay, this is 1. Okay. So you have two observers coming from the right and from the left. And because the value, they agree, this value should be 9. So this should be 9. Okay. So we, in a way, we kind of looking at this kind of problem from the graph. Okay. And let's see some more example. In fact, x closer to A, this is the constant functions. Is always the K itself. Okay. So this is a kind of uh, trivial things to do. All right, so what about this one here? Say 3x plus 1. Okay, so this is the another example when you can just, well, you learned one in your high school in calculus. When learning limit, you just try to plug in the numbers. Okay, that's right. You just plug in the numbers, then you get uh, here you have 3, 4. Okay, so here's your f of x. Okay, if you deal with this pictorially, 3x plus 1. So 1 here, 3x is there. 1, this is 1/3. 1/3. Okay, so when you equals 1, see here, observer from the right, observer from the left, agrees and the value of c is 4. So the limit is 4. Okay. In fact, the more general thing is that x equals a, say this is mx plus b, right? Just plug in the numbers, ma plus b. Okay. Okay, so that's the first rule of thumb. When you can plug in the number, then that's limit. Okay, here you can plug in the numbers 1, and when you get the number, that's limit. Okay. So for example, you can have more complicated function, for example, sorry, more complicated limit. So it's -2, say minus 3x okay, and you try to plug in the number here. Okay. Of course, there's the value. When you plug in the number, here you get -3, -2, power 4. Okay. So what you get here? 2 to the power of 4, 4, so 16. 16 times this -3, 48. This is 4, so that's 28. This is 5. Right, you can compute that. -20, so -15. Okay, just plug in the number. For something that you cannot just plug in the number, for example, the one that we have earlier. Okay, so let me just comment here. Plug in x equals 1 because it is undefined at 1. because undefined at. See? All right, so what do we do here? Okay, so let's just do factorizations. Okay, and use the limit. All right, when we write something like this limit, implicitly, it means that x not equals to 1. Okay, so if you assume x not equals to, sorry, this is -1. So when x not equals to 1, then this shouldn't be 0. Okay? So you can cancel. Okay? So you get limit x equals to 1, x plus 1. Right? So, but this is the case of, let's see, back to the case like this one. When you are able to plug in the number. Okay, you plug the number, so you get 2. That's limit. Okay. So as long as you can plug in the number, then you're okay. So that's the limit. So that's the computation of limit. Let me try again to find some more example. Okay. Another example is this one. Okay, let's do this one. Let's compute this limit. Square root of x plus 4, x minus 2 to the fourth over 3x minus 6 squared. Okay. Let's do some computation here. First step should be try to plug in 4. You get a number, but when you plug in 4, you're stuck with this one because as you plug in 2, so 3x minus 6, right? So this gives you 0. Okay, so you just cannot plug in x equals 2. Right? So somehow you have to simplify. Okay. So let's do some simplifications. Okay, so what you observe, how we should simplify. Okay, are there any, let's see, the same factors, up and down, numerator and denominator are the same factors. Observe first. Okay, see here, while the top the same, you can factor 3 out, right? So you take 3 out, so this x minus 2, so it's square. So this should be a square also. Okay. Sorry, the OneNote stuck. Let me just OneNote. Okay, just share again. Okay. Okay, here, so last one is take the 3 out. So this is that's 2. And you square this because you square. Okay, so what happened here? So this is 3, x minus 2 square. Here you have x minus x to the x minus 2, same factor, but power 4, but inside is square root. So it also has power 2. So they cancel. Okay. So you end up with the, and here you get 9. Okay. So that's after simplifications. This becomes c square root of x minus 4. Oh, plus, sorry. Yeah. Okay, over 9. Now you can plug in a 2. This makes sense, right? So square root of 6 divided by 9. Okay. Okay, so there's one thing you can do with this one. All right, so let's see. This kind of computations. 6. Let's do something slightly different. Here. All right. So let's first attempt to plug in h equals 0. Right. So when you plug in x 0, you get what you get. Well, the denominator you get 0, and if you plug in 0 here, you get 2 square minus 4. This also, well, this is undefined. So you somehow we have to simplify this first. When you simplify, how you simplify this? Let's just carry on the computations, because this is 4 minus, let's see, this is for h plus, and you have h squared minus 4, right? And Now this for cancel. Okay, so you end up with this one. You can take the h outside, so you have 4. There you go. Okay, so let's continue these computations. So you get limit. So end up with this. Well, this tells you that h not equals 0. S gets closer to 0, but it's not 0. So because it's not 0, you can cancel. So eventually you ended up with this. Well, now you can plug in 0. You end up with 4. Okay. So let's see some computations. Okay. Let us define some one-sided limit. Okay. So just intuitively say something like this. Okay. So first for this 1, this is 2. Okay. So in this case, if one observer comes from the right and gets closer to 2, in this case, there is no limit because the observer from the right and from the left don't agree on a number. Yeah. But you see that in this case, we say that limit x approaching a from the right is 2. Okay. X approaching a from the left is 1. Okay. So that's the picture. And the value of a can be somewhere else. For example, here. And f of 3, f of a is 3. Right, so three numbers. So the observers from the left and right don't agree, and the value of the functions are also different. Okay, so this is the theorem. Okay, so let's see what's up. Let's see. We have the x plus l if and only if the one-sided limit equals to the one-sided limit, also same thing. Okay, so let's say that limit exists if one-sided limit agrees. Okay. Limit exists if only if one-sided limit agree. Okay. All right, so just one example here. Example 7. This is from the exercise in the book, actually. So we have there. The value is this. All right, sorry, it just got stuck. Okay. Okay, here. Here you have but here you have okay, so this number is -1. Here is sorry, this is -3. This is -1. This is at 1. Okay, this is say 4. This is 3. This one is say 1. Okay, so in this case, what we can say is x goes to -3 from the left. From the left is, let's see, this is 3. Okay. Going to -3 from the right is, let's see, this is 1. Okay, but f -3 is actually 1. See the solid dot here. What about at 1? Well, we compute this at -1 from the left. From the left, it is 3. Okay, from the right, sorry, this is from the right is also 3. Okay, and f of -1 is actually 3 also. Okay, and what about this x going to 1 from the left? From the left, the value is 1. Okay, What about this one? Well, because this is extreme oscillations, the limit does not exist. Okay, while the f1 itself is just defined here, is a value 1. Okay, so what can we say about this is, well, one-sided limit exists, but from here we know that actually this does not exist. While in the second example, this tells us that is they are the same. So two observers getting a same number. Okay. Limit doesn't exist in this case. Okay, so let's see the idea of the limit. Questions? Example. Find the limit x minus 1 for x, but 1 has okay, so going to 1 you just cannot plug in the numbers. Okay, but we compute the one-sided limit. Okay, so they changed the sign at x equals 1. Okay, so the absolute value, remember the absolute value? That equals to x minus 1. And to the left, so divide it to, say, 2 rooms like this. Okay, so observers coming from the right okay, so it's coming from the right, the absolute value is just x minus 1 here. So they cancel. Right? So just give you 1. Right? However, another observers coming from the left here, see this absolute value as 1 minus x. So this gives you negative 1. Okay, so even though the one-sided limit exists, but they don't agree. So the conclusion is that this limit does not exist. Okay. All right, any questions? All right, and so that's sample 9. Let's do limit with with this one. So it's supposed to compute this limit. So going for one from the right of square root of x minus, remember this function here? Correct. So the rounding down. Okay. All right. So in this case, let's see here. This is 1. So the observer is coming from the right. So you will pass, for example, pass this 2, maybe pass this 3. Okay. Okay. As this one passed 2. Okay. So you see, passes 2 to the right of 1. What happened to this one? So the value of x is on here. So you round this down. So it becomes 1. Okay. So as x gets close to 1, this value is 1. Okay. This value is also, so that's 1. Okay. For x. We have x equals to x minus 1. Sorry. Okay. So in this case, eventually it becomes this limit. Now you can plug the numbers. Well, it's defined because this x is larger than 1 because you subtract 1 here. So x must be larger than 1. Okay. So this is positive. So x going to 1 from the right. So this is 0. Okay. Questions?
Sir,
Yeah.
I'd like to ask,
Uh-huh.
it says that as x passes 2 to the right of 1, but why is the interval only 1 until 2, not 1 until 3?
Oh, okay. Here, if you come from to getting closer to 1 from the right, you pass every numbers here, right? 10, 9, 8, right? And the value of this floor of x also decreases, but discretely, right? Because you pass 10, then the value would be 9. Past 9, then it would be 8. Past 8, then it would be 7, right? It's getting lower, the value. Okay. And from, well, eventually you pass 2. Okay. You pass 2. And when you round the floor of this x here, so our x now is here. So we don't need to consider x far away from 1. Okay. just consider x getting close to 1. So in this case, yes, to the left of 1. Okay, so when you all right, let me just write down something here. Make this bigger. Let's put a different color. Just one. Start from 1, 2, 3, 4. Okay. Over here, we compute x, right? Okay. Over here, what you compute is minus 4, right? Over here, what you compute is x minus 3. Here we compute x minus 2. All right, are you with me at this point?
Yes, sir.
Because this is just a round down of number x here. This is 3 is a round down floor of what x here. And eventually you pass 2, then it becomes this. And when you approach 1, then you just cannot avoid using this one. And we just use the last one. You don't need this one. You don't need this one. You don't need this one. Right? Because eventually you pass 2 anyway. Okay?
Thank you, sir.
So when you say in these notations, say 1, okay? You don't need to consider x going far, like from 1,000 and then 500, something gets close to 1. You just need to consider something like this one, very close to 1 actually. Right? So then that saves lots of energy, right? So because you don't need to consider far away from 1. Don't need to consider x far away. Okay, so you just need to something that's closer to 1. Okay, so then that's the idea. Okay, one more example before we stop. Okay, here's just limit x getting 0. Okay. All right. So this notations tells you that x not equals to 0, but just gets closer to 0. So x just very small number to the right. So means positive. Okay. X positive and to the right. Okay. So what happened to here's the same case. Over here, this equals to 2. Here equals to 1, right? Because you round down. Here, that's 0. So you don't need to go far away from 0, it just gets closer. So we just need to use this one. Okay. All right, so what happened to this one? Well, this just becomes, this just 0, it's just x, right? So then that's equals 0. right? Why 0? Because this is 0. Okay.
I want to answer.
Sure. Go ahead.
It's divided by x. Why don't we compute the x for the divide? So 0 divide by 0 like that.
Now, this not the, all right. Uh, okay, here's the catch. Let me just give you one example. Here, this 0 here, 0 is absolute 0. What do I mean absolute 0? Just because the number 0, it's not limit. Okay, because 0 in the context of limit is not 0, because here you have, if we say something like this, right? This is correct, right? Because this is a simple thing. But this 0 is not absolute 0. This is 0 in the context of limit. Okay, so this limit is actually, say, positive number, but really small.
Okay, I get it.
Okay, and this is just because this is not the context limit. This is just really 0, 0, nothing. Nothing divides by something. It's nothing. Okay.
Okay.
We'll emphasize on this concept later because this is important, but it's a good question, actually. But we haven't gotten to that stage yet, but we'll get to that one. All right, more questions? All right, if not, then we'll stop the record and